Hello, everyone. Welcome to AI4. Our next session is going to be led by Mark Sherman. He is the Technical Director of Cybersecurity Foundations at Carnegie Mellon University. Please join me in welcoming Mark to the virtual stage as he turns on his video and starts sharing his screen. All right, take it away, Mark.
Thank you, Patricia. Very good. Welcome, everybody, to this presentation of threats to machine learning applications. Happy you could join us today. Just to give you a little background of where I'm coming from when we go through this material, I'm on the research faculty at Carnegie Mellon University, which has a lot of cybersecurity work, computer science work, artificial intelligence, and the combination of those leads to us redoing research in how you want attacks and defends new kinds of machine learning systems. In particular, I'm part of what's called the Software Engineering Institute. That is a Department of Defense funded center focusing on software engineering, cybersecurity, and artificial intelligence. And again, what we're talking about here is really the intersection of those. It's been around since 1988. And it's a reasonably sized organization. We have about $145 million in funding, supporting staff mostly in Pittsburgh, but also in the Washington, D.C. and other areas. So the CERT program in particular, which is where I'm the technical director, is really about understanding cybersecurity issues facing the federal government, the Department of Defense, Department of Homeland Security, similar kinds of organizations, to defend the country against cybersecurity attacks. And for that, we carry out a wide variety of research, one of which is what I'm going to be talking about today. So if you go to other talks about understanding attacks on machine learning or threats to machine learning or vulnerabilities of machine learning systems, you will frequently see some very common pictures. Pandas that look like gibbons, stop signs with little white squares that look like yield signs, turtles that are interpreted as rifles, a t-shirt you can put on that makes you invisible to facial recognition systems, glasses that you can put on that make you look like Mila, or make anybody actually look like Mila Jovovich. I'm not going to be showing you all those little pictures. I'm not going to be running through examples of how these systems, the images that are used to defeat those systems. You can search on the web and find any of those. My intention here is to give you an understanding of what's going on under the covers. Not detailed mathematics. I'm not going to be going into the statistics of how all this is done, but to give you an appreciation of where these attacks happen, why they happen, what you can do about them, and how that fits into the larger scheme of vulnerabilities in building these kinds of systems. And frankly, to enable you to have a good discussion with the technical staff members that you will likely have on your team who will be delving into the mathematics and the statistics involved behind this, so that you can understand what kinds of questions to ask and they can get the direction from you that'll help them build the kind of system that you want. So let's start by understanding the machine learning attack surface. To talk about this, we just need to have a general discussion of what these systems are and how they're built. Again, I'm not going to go into any of the real math here, so you can ignore all the funny symbols that are there. If you do want to look at the math, the reference in the bottom is where this figure comes from, actually has hundreds of pages of going into various mathematics of each of those boxes, how they're implemented, and so on. We're not going to do that here. I'm more interested in using this as a vehicle to explain the various places that these kinds of systems can be attacked. So if we start at the very beginning, when you build these systems, they need examples to look at. What are called training data, basically. And what that is a subset of really the data that's out in the world. So let's pretend we're going to build something that's going to distinguish between oranges and bananas. So you need to have a bunch of pictures of oranges and bananas. That's a subset of all the pictures of all the oranges and all the bananas that are out there. You have to pick some subset in order to build your system. And that's the first point of attack. You could start slipping in other kinds of pictures besides bananas or oranges. You could slip in more oranges than bananas. This is the place where you sometimes hear biases being introduced. So facial recognition systems that are trained only on white male computer scientists based in Silicon Valley as a general facial recognition system is one of the more popular examples that people talk about. But it's also a place that adversaries can attack. As it turns out, there's one subset of these kinds of systems that use something called active machine learning. Those are systems that react and change their analysis based on input that's given to them. If you have someone that then tries to feed bad input with the idea of drifting how the machine works, you can wind up with something that looks very bizarre. A recent example of this is the Microsoft chatbot, in where it basically learned how to swear and be very racist. So picking the right subset of domain is one place that you can attack it. You can attack it by figuring out which measurements and altering them. So take, for example, our bananas and oranges. You might say the two things to look at are how long the fruit is and what color it is. If you pick something or force something to be picked that's not very distinguished, then again, you can subvert the system. Once you have measurements, then you need to do features. Features are based on measurements. So let's again talk about colors. You may not necessarily look at the colors. You may look at the Fourier transform of colors. You know, how bright is each individual piece of the spectrum of that color. If you can force that into something that will pick something that you don't want. So if you have you want to hide a fruit, for example, by putting a red spot on it and it's only looking for yellow colors, then the feature selection process will be subverted. And that, of course, leads into the features of the subset. Having picked what you want, you then have to calculate what that is from the actual measurements. If that gets subverted, then although you might have legitimate measurements, you'll wind up with illegitimate features. And there's a whole large body of science as to how you go about picking those features. Once you have a collection of data, pictures of oranges and bananas, you actually split that into two parts. One part you're going to use to teach the system to recognize oranges and bananas. The other one you're going to use, as we'll see later, in order to evaluate how well it makes that distinction. If your training data is not representative of the domain, you pick something that not really is the same collection of oranges and bananas, then the system is going to recognize something that's very different. A historical example has been there was an attempt to build a system that could recognize tanks. It turns out all the tank pictures they had were in the forest. They put this out in the desert to recognize tanks, and it didn't because it recognized forests, it didn't recognize tanks. The training data didn't really represent what you wanted it to represent. Similarly, the algorithm that's used for taking that training data, if it tries to slip something into the model that's not correct, for example, it has built into it, let's pretend, that in addition to bananas and oranges, it also will recognize apples. And if it sees an apple, it'll try to fool you, so it'll say, I'm going to call that an orange. And it's another way to subvert the system. Similarly, we take a look at the testing data. The testing data is actually divided into two parts. The training usually don't divide it this way, but one of them is the actual pictures of oranges and bananas. That's the test data. And as we'll see later, there's the labeling of that data. So you mark each picture whether it's whether it's an orange or whether it's a banana. And then you're going to see whether the system works well or not. And for those who know this, this is supervised learning, but the model can be generalized, and just take my word for it that it works for a lot of other models as well, whether you're doing clustering or classification or all the other variants here. But we're just going to be simple here and say you have the labels of which are bananas and which are oranges. Again, if you feed bad test data in, you alter the test data, you're going to wind up with something that's bad. In particular, if you also put the wrong label on, you have this banana, but you label it an orange, then the system can be subverted as to what it thinks is what color fruit. The model that gets built, think in this case of conventional compilers. You compile a program, and the program, as it's being built, also slips the malware into it. That's happened in the past in China and other places. Same thing can happen in machine learning, in that the model that gets built can have some additional code in it that actually is looking for something else besides apples and oranges. And finally, the evaluation criterion. That is, how you decide whether what you've built makes sense or not can be altered. That's called the loss data. Again, above, you have built something that can distinguish between apples and oranges. Bananas and oranges. On the bottom, we've run it through, and we've compared what the model predicted was banana and orange versus we have truth here. That's the bottom path. as to what really are bananas, what really are oranges, and we can compare how well they match. If you can alter that loss function so it looks like it says that you're doing something really good when you're doing really bad, you have, again, subverted the system. So there's a very big attack surface, lots of places that you can get at the system that can alter its behavior. Now, there's a particular kind of attack surface that's somewhat unique here that people can exploit just because of the mechanics of how these systems are built in practice, rather than the somewhat theoretical model of attack that we just went through. And that's by using something called transfer learning. And to discuss transfer learning, we have to spend a little bit of time going into what really is underneath the covers here. Not a lot, I promise you, no formulas are going to pop up here. But the idea is you have deep neural networks, you have input layers. Those are, if you like, the pixels of the picture showed here. You have output layers at the far right, which is the actual selection of what the face is. And what's happening in the middle is it's selectively getting a better understanding of the data. So the first layer might be looking for edges in this example. In the second layer, maybe combinations of edges, ears or noses or something. The third one starts to identify put together faces, and the output layer actually says this is John Smith. This is the general structure of these things. Mind you, this is just a picture. You may have dozens and dozens of layers. You could have each layer having 1,000 nodes in it. So in practice, these are really quite big kinds of systems. Now, to understand how they get subverted or how they can be subverted, I have to take you one more level down. The way all those nodes work is they do calculations on numbers attached to those edges and numbers attached to the nodes. And those numbers change as the model gets trained. The calculations for doing those changes vary. That's part of what the statistics involved are, was something that your data scientist can help sort out as to how you pick it. But nevertheless, the general idea is to keep putting more information in until those levels get somewhat stable and the output matches the loss function you're willing to say. That is, the outputs coming out of the far right side are good enough compared to what you want to accomplish. Now, mind you, this is or can be enormous. Recently, GPT-3 was just released, which is a deep neural network having to do with text generation, actually. But again, for our purposes, a good example. It has 175 billion parameters. That's billion with a B. So you can appreciate there's a lot of calculation that goes into building one of these. It's very hard to have the resources necessary to build such a system every time you want to build a machine learning application. So instead, what people frequently do is something called transfer learning. And it starts with an existing neural network. And that's usually called the teacher network. So here we have an abstract network. Some input comes in. We have all of our layers. It produces an output. Say, for example, the system that we just talked about, the various image recognition systems that Google has put out, that other people have put out. And you can use these as a beginning. What you then do is you say, I'm going to make something that's very similar to it by copying all but the last layer. The last layer that's finally made the selection of orange versus banana, I'm going to rebuild from scratch. I'm not going to keep that one at all. Instead, I'm going to take all the previous ones and reuse them as part of my new neural network. And so instead of having to set all those 175 billion parameters from scratch, I'm going to reuse the ones that are already there. And the way that it works is I get to also slightly tweak how much I want to retrain. So although I will always replace the last layer with what I want for my particular decision, bananas versus oranges, I may choose to also let some of the last couple of layers also be altered as I train. Remember, the way these systems work is you start with some system that has those numbers put in, you feed it some more data, it changes those numbers as it learns more and more. In this case, the student, the derivative machine learning system, will allow the last several layers to be changed, but not the first couple of layers to be changed. That's the general idea behind transfer learning. Now, when you do something like that, you can do something called deep layer feature extraction. That's if you have something that's really close. So I have bananas and oranges. I want to build a system that's bananas and apples. So you can say, well, the analysis is probably really, really close. And so I'm just going to change that very last one, build that very last one. So it's very cheap to train, certainly compared to training all those other thousands of nodes that are already there. And you get reasonably good accuracy. Now, the challenge from a cybersecurity perspective is that the adversary has deep knowledge of the teacher. It understands all those parameters that are there. And as we'll see later, understanding those parameters gives insight as to how you can generate models, pictures, or images, or input that will fool the machine into picking up the wrong information. So it's very easy to create adversarial input because what could fool the teacher could very likely fool the same kind of student. It's also very easy to exfiltrate the model. By that I mean this model could have proprietary information in it. You have lots of pictures of parts that are good and bad that you've used in order as part of your QA process. That might be proprietary information. By knowing that you started with a particular teacher, an adversary could extract out that information and basically work backwards to figure out what the data were that allowed you to make that distinction. And now they have the ability to do the same kind of QA that you were doing. At the other extreme, there's something called full model tuning, in where you start with everything that was done by the teacher, as opposed to starting with all zeros or random numbers. And you retrain, or you allow all of the layers to be adjusted as you feed in new data. This is better when they're not close. For example, we had bananas and oranges. Now I want to separate cars and trucks. You may not know that, but it's actually very practical to do that, that if I have something that distinguishes bananas and oranges, it actually has a lot in common to be used for separating cars and trucks. So you can, it makes a lot of sense to do that in practice. You will get a better accuracy than with deep layer feature extraction for those kinds of domains when you actually have cars and trucks rather than oranges and bananas. And it's more resilient to these teacher-specific attacks because you've now tweaked all of the initial layers as well. The downside, as you might imagine, is it's very costly to train. Not as much as it costs to train the teacher to begin with, which may have had millions of samples put into it. You're going to put in thousands in order to do the retrain, but it's still much costlier than the other attack. And as true in most of these kinds of situations, there's an intermediate. You can only train the last handful of layers. Its accuracy, again, will depend on how close the teacher and the student domains are. And again, there's the trade-off. You get better resiliency than deep, but not as good as full. It's more costly to train than deep, but it's cheaper than full. So this is in order to help your data scientists figure out what the best choice is. You need to understand what kind of trade-offs you might want them to implement on cost versus accuracy. So now that we've understood the general attacks, and in particular the risks that come from transfer learning, let's talk a little bit about how one deals with it. And by this, again, I'm not intending to go into a lot of math, but I do want to give enough of background so that you can understand what trade-offs the engineers have to make in order to build a resilient system. And to do that, we have to talk a little bit about classifications. So let's pretend on the far left, we've got 4 pictures, 2 bananas, 2 oranges, for sake of argument. Each dot represents one of those pictures. And our feature space here, the thing that you're going to train the system against, well, again, not marked here, but we'll make it simple. Say one axis, the vertical axis is color, and the horizontal axis is the size of the fruit in the picture. So again, you collect this together. We run it through this deep neural network that we've created. And what comes out is basically a mathematical function, but I'm going to show it graphically here. And what you see is an area of that graph where if you get any new pictures in that top figure, you're going to call it an orange. You get any figure dot in the bottom figure, you're going to call it a banana. And this is the kind of thing it does. There's, again, many, many different algorithms for figuring out what that shape should be and how big it should be and how you go and how fast it is that you can calculate that. But that's basically how classification works and what comes out of the system. So what do attacks look like here? Well, you can have something called an inclusion attack, and that's where something that's there that shouldn't be there. So you think you're looking at an orange, but it's really a banana. We have exclusion attacks, something that really is a banana, but didn't get classified as a banana. In this particular example, I have the ability to say it's not either space. There are other systems which will divide up the space so that everything's always classified. You feed it a picture of a truck, and it will classify it as an orange or a banana because it always has to make one of those two choices. And there's a whole nother range of technology and discussion about how one can say, I don't know, in these kinds of systems. So again, for simplicity, the two basic kinds of attacks are inclusion and exclusion. Now, you might notice that those both happen because of what you can think of as the spikiness of those areas that are used for the classification. If you can somehow cut off those spikes, then you can mitigate attacks from undesired inclusions. If you enclose those spikes, you can mitigate against undesired exclusions. So now you won't get the banana called an orange, but you will get the banana that is supposed to be a banana. However, there are lots of ways to do that, and they all have trade-offs, sometimes in accuracy, sometimes in resiliency. Some of the ways that you can actually carry out those exercises is you can add adversarial examples in the training. You can train with a larger domain set. You can calculate the convex hull. That's a way to fill in the spikes. You can apply statistical robust regression. Robust here is a statistical mathematical comment, not a cybersecurity comment. If you like, that's a way to cut off those spikes. But all of these trade resiliency for accuracy. Adversarial examples are noisy, and so they introduce noise, they introduce possible errors in the system. You can have overfitting. That is feeding it more data, but that tends to create even more ragged boundaries, the things that we were trying to avoid. But the concave boundaries could be legitimate. You do want to exclude them. And the looser boundaries could be legitimate. It could be that you did want to include them. And so these are choices that the person building the system can make, and you can be a lot more precise as to how many differences you're willing to take in the system, how many changes in pixels that shouldn't be there should be included or excluded. Again, there's a lot of different algorithms and math behind this, but being able to understand and appreciate what's going on here is a way to explain to the engineers the trade-off you're willing to make between accuracy and resiliency. An entirely alternative approach, of course, is to use redundancy, having multiple systems, each one independently coming to a conclusion using some kind of voting. That obviously has a lot more expense to it. So those are ways that can be attacked. How does that actually happen? Well, it turns out that machine learning systems are subject to the same attacks that existing applications and software are. So for example, you just badly write the system. There'll just be programming errors. And so, for example, TensorFlow, one of the more common of these machine learning-based systems, has problems in it that create cybersecurity vulnerabilities. You have problems with supply chain. Given that the data and these teacher systems, if you like, are coming from places that you really don't know, you don't know if an adversary has slipped in some bad data, some bad algorithms, or both. And these are just some of the common places that people can get things. And there's no real way to check the provenance of what you've got. And in fact, we already know that there's a huge supply of deep fakes that can be used in order to feed these systems in order to try to fool them what's going on. But worse, we actually can't identify those deep fakes. That some of the material that's coming in that you might be training your system on could be fake, and you wouldn't know it. So how do you do that? Well, there's a whole collection of cybersecurity that's worried about supply chain risks. I won't go into the SPEEDO process here, the supplier product distribution operations method, but you can apply this as a way to mitigate the kinds of things that you can do for supply chain risk. There's the denial of service attack. That's where, just like any other kind of denial of service, you have many people pounding on the system and thereby preventing legitimate users from getting access to it. You have integration points. Machine learning systems are rarely standalone applications. They feed into other systems. And the academic studies have said that those interconnections are one of the two most common ways by which systems can be attacked. The other way, if you're curious, is simply the popularity of the system. And when something's really popular, then obviously hackers want to go after it. From a technical point of view, it's these interconnects that provide the place that you can sneak in the attacks. And of course, there's the human element. Your insider could be implementing all of those things we talked about earlier: the test data, the training data, the loss algorithm. By understanding that you've got real human beings building this, you can put in whatever facilities or processes you'd like in order to mitigate those issues. And there's a whole variety of information about that. Again, I've included some at the bottom here. Finally, given AI systems, there's this whole concept of what I call fake news, basically the untrustworthiness of AI systems. People ultimately will be seeing the output of this, and the reasoning from these systems is opaque. It's a billion numbers that somehow said that's an orange or that's a banana. There's no real way for it to explain how it came to a decision. And when you're making a decision about whether someone should go to prison or not, when you're making a decision as to whether a house should be checked for lead or not, people want to understand. And when they don't, they can get very frustrated. And in today's environment, people can amplify these misgivings, whether they're legitimate or not. There are some legitimate ones, there's a lot of illegitimate ones. And as a result, you can put a lot of fear and uncertainty and doubt, and people won't trust the output, even though in many cases it might be very good. In fact, Gartner did a survey where they said that 80% of the line of businesses expect to override their business decisions made by AI. There's no good answer here. We need to, at the technical side, improve the explanations, and the social side, explain, like I've tried to start here, as to what the vulnerabilities are, what the trade-offs are, but fundamentally recognize that machine learning is statistics. Unlike your payroll system or unlike your bank account, there is a single answer as to how much money there is in your bank account. It is something that can be checked. It's something that is objective. Here, we're talking about probabilities. What are the odds that I really recognize the banana? Or what's the odds I really recognize an orange? And under what kind of assumptions? Understanding that this is a different kind of world and that there's always engineering trade-offs, no truth, is really key to understanding how you mitigate vulnerabilities. So I appreciate the time you've spent. We've gone through the academic places of where you can attack, in particular, the details of how you can attack transfer learning, the general idea of how you worry about inclusion and exclusion attacks, and then how those get realized in practice through conventional threats. We do a lot of work here at CMU and the Software Engineering Institute and CERT, carry out enormous amounts of research here. There's lots of places you can get more information. If you want a copy of these slides, please contact us, as you see at the bottom, at info@scI.cmu.edu, and we'll be happy to give you a copy. And otherwise, I'm happy to take your questions. Thank you.
Awesome. Thank you so much for that wonderful presentation. It was really insightful and I learned a lot. So everyone, please give a big virtual round of applause. Woo! All right. So you can feel free to head to your next sessions and check out the agenda if you're not sure where to go next. Also feel free to take advantage of our networking sessions that we have available. Thanks so much and we'll see you soon.